Assalamualaikum warahmatullahi wabarakatuh. Good day, CBP students. My name is Mahid M. Mangontarum from the Mathematics Department. I am one of your lecturers for the 2020 College-Bound program. Today, we are going to discuss Chapter 4, which is on equations in one variable.
These are the topics to be discussed: the introduction, linear equations in one variable, quadratic equations in one variable, and equations containing rational expressions. There is also section 4.5, which will be discussed in the next video lecture. We will start with section 4.1, where we are going to define what are equations and cite some reasons why they are important. So why do we need to study equations? Well, equations are very important because they have a variety of applications in real life. Note that mathematics plays a vital role in understanding the world around us. From complex topics such as modeling of real-life phenomena to solving basic word problems, we utilize mathematics. In particular, mathematical equations help develop the creative capacity of the intellect, and finding solutions to equations promote critical analysis, which are both substantial in the better performance of our respective careers. An equation is defined to be any mathematical statement that asserts the equality of two algebraic expressions. Let us consider the phrase sum of 6 and 4. In symbols, we may write this as 6 plus 4. Another one, the sum of a number and 4, can be written as x plus 4, where x is an arbitrary variable. From the previous discussions, we know that these two are called expressions. The first one, being composed of only numbers, is a numerical expression, while the second one, because of the presence of the variable x, is an algebraic expression. So how about the statement, the sum of a number and 4 is 10? This can be divided into two parts. We know that the sum of a number and 4 is x plus 4, while the second part can be written as equals 10. The resulting mathematical statement is an example of an equation, where x plus 4 can be labeled as the left-hand side and 10 is the right-hand side. To continue, we define a solution to be any value which, when substituted to a variable, makes the equation true. The set containing all solutions is called a solution set. Looking at the previous example, the equation x plus 4 equals 10, we immediately recognize that x equals 6 is the solution because it is the number which, when added to 4, gives 10. Thus, the set containing 6 is our solution set. When two or more equations have the same solution set, they are called equivalent equations. For instance, x plus 4 equals 10 is not the only equation whose solution set is the set containing 6. See for example, 2x minus 7 equals 5. Note that when x equals 6, 2 times 6 minus 7 is equal to 5. Thus, 6 is also a solution to this equation. This means that the two have the same solution set, which basically means they are equivalent. Before proceeding, we note that solving equations simply means finding their solution sets. Finally, We define a replacement set as a set of numbers for which an equation is defined. Usually, we take as replacement set the set of complex numbers or its largest subset for which a given equation makes sense. We have three more important terminologies, namely identity equation, conditional equation, and contradiction. So if the solution set of an equation is equal to its replacement set, the equation is identity. When there exists an element of the replacement set that is not a solution to the equation, then it is conditional. Lastly, if the conditional equation is never true for all values in the replacement set, then it is a contradiction. In this case, the solution set is empty. We will now proceed to section 4.2, where we will discuss linear equations in one variable and how to find their solution sets. A linear equation in one variable is an equation of the form ax plus b equals 0, where a and b are real numbers and a is not equal to 0. This equation is in standard form where there is only one variable, the variable x. These types of equations are also referred to as first-degree equations in one variable. They are called linear or first degree because the highest power is 1. In solving these equations, we make use of the addition and multiplication principles. The addition principle states that if a and b are equal, then the results after adding c to both sides are still equal. Similarly, multiplication principle states that if a and b are equal, then the results after multiplying c to both sides are still equal. Apart from these two principles, we will also make use of some concepts which have already been discussed in the previous video lectures. In particular, we will use some of the properties of the real numbers and the operations on polynomials. Now, suppose you are asked to solve the linear equation 2x plus 4 equals 0. To solve this, we will do algebraic computation to find the value of x. That is, by addition principle, we will add negative 4 to both sides of the given equation to get 2x equals negative 4. This is because 4 plus negative 4 equals 0 and 0 plus negative 4 is negative 4. Next, we multiply 1/2 to both sides so that we have x equals negative 2. And though it is not part of the solution, we may also check if this is correct. Notice that when x equals negative 2, we have 2 times negative 2 plus 4 equals 0, which becomes 0 equals 0 after simplification. Therefore, the solution set is the set containing negative 2. Let's have another example. We have 5y minus 2 times the quantity y plus 1 equals 2 minus 3y. To solve this, we need to simplify first. Notice that in the left-hand side, we can apply the distributive property of multiplication over addition to get 5y minus 2y minus 2 equals 2 minus 3y. Next, we add 3y to both sides to get 5y minus 2y minus 2 plus 3y equals 2 minus 3y plus 3y. And since negative 3y plus 3y equals 0, we get this resulting equation. Here, the first three terms in the left-hand side are like terms. So by addition and subtraction of polynomials, 5y minus 2y plus 3y equals 6y, giving us 6y minus 2 equals 2. Again, we add 2 to both sides to get 6y equals 4 because negative 2 plus 2 equals 0. Finally, multiplying both sides by 1 over 6 gives 4 over 6 or 2 over 3. Therefore, the solution set is the set containing 2/3. For another one, solve 4x minus 5 times the quantity x minus 1 equals 1 minus x. By DPMA, we get 4x minus 5x plus 5 equals 1 minus x. Combining like terms, we have negative x plus 5 equals 1 minus x. Adding negative 5 to both sides give negative x equals negative 4 minus x. We use again the addition principle and add x to both sides. However, this results to 0 equals negative 4, which is a false statement. This implies that the equation is false no matter what value of x is assigned. Therefore, the solution set is empty or null set. How about the equation 2 minus x plus 4 times the quantity 1 plus x equals 3x plus 6? By following the same algebraic computations applied in the previous examples, we arrive at 0 equals 0, which is a true statement. This means that the given equation is true for all elements in the replacement set. Therefore, the solution set is the set of complex numbers. Now, we have section 4.3 where we will learn about quadratic equations in one variable and the different methods for solving them. A quadratic equation in one variable is an equation whose standard form is ax squared plus bx plus c equals 0 for all real numbers a, b, and c, and a not equal to 0. They are also known as second-degree equations in one variable. The term quadratic or second degree comes from the fact that the highest power is 2. In solving these quadratic equations, we must first write the given in standard form. For example, if you have the following equations, you must write them in their corresponding standard forms. The process for this is left as an exercise for the students. Unlike the linear equations in one variable, here we have several methods to choose from when solving for their solution sets. The following are the methods of solving quadratic equations in one variable. We have by factoring, by taking square roots, by completing the square, and by quadratic formula. In solving quadratic equations by factoring, we will use the zero-factor theorem. This theorem states that if the product of two real numbers a and b is 0, then either a equals 0 or b equals 0. We also need to be acquainted with the special products and the methods of factoring. It is highly suggested that you review the said topics. Suppose that we are asked to solve x squared minus 7x plus 12 equals 0 by factoring. Now, it is easy to see that the left-hand side is a trinomial which can be factored into x minus 3 times x minus 4. Since the product of x minus 3 and x minus 4 is 0, then using the zero-factor theorem, we have x minus 3 equals 0 or x minus 4 equals 0. Solving for x, we get x equals 3 and x equals 4. Therefore, the solution set is the set containing 3 and 4. Another example, consider 4x squared minus 9 equals 0. Note that this equation can be written as 2x quantity squared minus 3 squared equals 0. By difference of two squares, we have the quantity 2x minus 3 times the quantity 2x plus 3 equals 0. By the zero factor theorem, we get 2x minus 3 equals 0 and 2x plus 3 equals 0, which give us x equals 3 halves and x equals negative 3 halves. Therefore, we obtain the solution set, which is the set containing positive and negative 3 halves. Now, suppose the given is 2x squared equals 9 minus 3x. Since this equation is not in standard form, we start by rewriting it as 2x squared plus 3x minus 9 equals 0. Applying factoring trinomials in the left-hand side, we get the quantity x plus 3 times the quantity 2x minus 3 equals 0. And by the zero factor theorem, we can equate both factors to 0. Solving for x gives us x equals negative 3 and x equals 3 halves. Therefore, the solution set is the set containing negative 3 and positive 3 halves. One more example. Suppose we have 3x squared plus 4x minus 2 equals 2x squared minus 6x minus 27. Clearly, we need to simplify the given by writing it in standard form. Applying the addition principle, we get this equation. Notice that we can combine the terms. For instance, 3x squared minus 2x squared gives x squared. 4x plus 6x is 10x, and negative 2 plus 27 is 25. This resulting equation can be written as the quantity x plus 5 times the quantity x plus 5 equals 0. Using the zero factor theorem and then solving for x results to the following. Recall that by definition of a set, the elements should be distinct. Hence, we will write negative 5 only once. That is, the solution set is the set containing negative 5. For solving quadratic equations by taking square roots, the following theorem is helpful. The theorem states that if x squared is equal to d, then x equals plus or minus the square root of d. Moreover, if the given equation is of the form ax plus b quantity squared equals d, then ax plus b equals plus or minus the square root of d. We can then solve the equation by finding the value of x. To illustrate, consider the equation x squared minus 25 equals 0. Note that this equation can be written as x squared equals 25. Taking the square roots of both sides give the following. We know that the square root of x squared equals x, but since x is an arbitrary variable, we consider the positive and negative square roots of 25. Thus, we obtain x equals plus or minus 5 and the solution set, which is the set containing negative 5 and positive 5. These steps right here are summarized by Theorem 4.3.5. Let's have some examples. Suppose you want to solve the equation x plus 4 quantity squared minus 16 equals 0 by taking square roots. First, we write the given as x plus 4 quantity squared equals 16. Using Theorem 4.3.5, we obtain x plus 4 equals plus and minus the square root of 16, which simplifies to x equals negative 4 plus and minus 4. This can be splitted into two parts, namely x equals negative 4 plus 4, which is 0, and x equals negative 4 minus 4, which is negative 8. Therefore, the solution set for this equation is the set containing 0 and negative 8. Another example, suppose the given is 3z minus 2 quantity squared plus 5 equals 0. If we write this as 3z minus 2 quantity squared equals negative 5, then by theorem 4.3.5, we have 3z minus 2 equals plus and minus the square root of negative 5. Recall that for any positive real number a, the square root of negative a is equal to I times the square root of a, where I is the imaginary number. This means that the square root of negative 5 is I times the square root of 5. Solving for z yields z equals 2 plus and minus I square root of 5 all over 3. Therefore, we have the following solution set. For the method of solving quadratic equations by completing the square, we recall from your special products the perfect square trinomials given by the following. In these formulas, note that when b is replaced with b over 2, we get a squared plus ab plus the square of b over 2 equals a plus b over 2 quantity squared, and a squared minus ab plus b over 2 quantity squared equals a minus b over 2 quantity squared respectively. In solving using completing the square, we have to check that the given is written in standard form. Also, the numerical coefficient of x squared should be 1. Only then can we use the modified versions of the perfect square trinomials. For example, if we want to solve x equals 3 minus x squared, we write it first as x squared plus x minus 3 equals 0. Notice that the left-hand side of this equation is not factorable. Also, it does not satisfy the form required when using the method of taking square roots. Hence, our option is to use completing the square. First, we write x squared plus x equals 3. Next, we take the half of the numerical coefficient of the middle term, square it, and add it to both sides. In this case, we add 1/2 quantity squared to both sides of the equation. Again, we add both sides of the equation with the square of the half of the coefficient of the middle term. Looking at our new left-hand side, it obviously satisfies the first perfect square trinomial. Hence, we may factor it as x plus 1/2 quantity squared. On the other hand, the right-hand side becomes 3 plus 1 over 4, which is 13 over 4. Taking the square roots of both sides give x plus 1/2 equals plus and minus the square root of 13 over 2. Solving for x yield x equals negative 1/2 plus and minus the square root of 13 over 2. Therefore, we have this solution set. For another example, take a look at 2x squared minus 6x plus 5 equals 0. As we can see, although the given equation is already in standard form, the coefficient of x squared is not 1. Hence, before proceeding, we divide both sides by 2 to get x squared minus 3x plus 5 over 2 equals 0. Now, both conditions are satisfied. In this equation, observe that the operation in the middle term is subtraction. This is a hint that tells us the potential use of the second perfect square trinomial. We then write the equation as x squared minus 3x equals negative 5 over 2. Here, we consider our b to be 3. This means that we add the square of the half of 3 to both sides of the equation. By the second perfect square trinomial, we get x minus 3 halves quantity squared equals negative 1 over 4. Taking the square roots of both sides, we have x minus 3 over 2 equals plus and minus I over 2. This gives us x equals 3 plus and minus I all over 2. Therefore, we obtain the following solution set. For the fourth method, let us consider the standard form of a quadratic equation in one variable given by ax squared plus bx plus c equals 0 for all real numbers a, b, and c and a not equal to 0. What will happen when we apply completing the square? Since a is non-zero, we can divide both sides by a, giving us x squared plus b over a, x plus c over a equals 0. We can write this as x squared plus b over ax equals negative c over a. Next, we add b over 2a quantity squared to both sides of this equation. Notice that this is precisely the perfect square trinomial where a is x and b is small letter b over a. Thus, we have x plus b over 2a quantity squared equals negative 4ac plus b squared all over 4a squared. By taking square roots, we obtain this equation. Solving for x, we have x equals negative b plus and minus the square root of b squared minus 4ac all over 2a. This is called quadratic formula. The formula that we have previously derived is actually this theorem 4.3.8. The said theorem states that the solutions to ax squared plus bx plus c equals 0 are given by the quadratic formula. For example, suppose we want to solve x squared minus 2x minus 3 equals 0. When solving equations using the quadratic formula, the first step would be to identify what are the values of a, b, and c. Looking at the given, we can see that a equals 1, b equals negative 2, and c equals negative 3. Thus, by direct substitution, we have x equals negative of negative 2 plus and minus the square root of negative 2 quantity squared minus 4 times 1 times negative 3 all over 2 times 1. Since negative 2 quantity squared is 4 and negative 4 times 1 times negative 3 is 12, we can simplify this as 2 plus and minus the square root of 16 all over 2. It follows that x is equal to 2 plus and minus 4 all over 2. Next, we split this into x equals 2 plus 4 over 2 and x equals 2 minus 4 over 2. These two equations would give us x equals 3 and x equals negative 1 respectively. Therefore, the solution set is the set containing 3 and negative 1. Another example, consider 3x squared minus 4x plus 1 equals 0. Like what we did in the first, we start by identifying what are the values of a, b, and c. In this case, a equals 3, b equals negative 4, and c equals 1. Using the quadratic formula, x is equal to negative of negative 4 plus and minus the square root of negative 4 quantity squared minus 4 times 3 times 1 all over 2 times 3. This can be simplified to x equals 4 plus and minus 2 all over 6. Thus, we have x equals 4 plus 2 over 6 and x equals 4 minus 2 over 6. This result to x equals 1 and x equals 1/3 respectively, giving us the following solution set. How about if the given is negative 3 plus y squared plus 2y equals 1 plus 2y squared? Clearly, before proceeding, we have to express the given in standard form. That is, negative y squared plus 2y minus 4 equals 0. From here, we see that a equals negative 1, b equals 2, and c equals negative 4. The quadratic formula then gives us y equals negative 2 plus and minus the square root of 2 squared minus 4 times negative 4 times negative 1 all over 2 times negative 1. Notice the use of the variable y instead of x. This is because the given is in terms of y. Now, by simplification, we get y equals negative 2 plus and minus 2i square root of 3 all over negative 2. As we can see, negative 2 is a common factor in the numerator and denominator. Hence, we can factor out negative 2, leaving us with y equals 1 minus plus I square root of 3. Therefore, the solution set is the set containing 1 minus I square root of 3 and 1 plus I square root of 3. We are down to section 4.4, the last section for this lecture. At this point, we are going to introduce what are equations containing rational expressions. When given equations contain rational expressions, they are called rational equations. Here are some examples of rational equations. In solving these types of equations, there is a step-by-step process. The said process will be illustrated in the following examples. Let us try to solve the first rational equation given by 1 over x plus 6 over x plus 4 equals 1. Because of the terms in the denominator with the variable x, the rational expressions in the left-hand side are undefined for some values of x. Thus, our first step is to define the replacement set. For this equation, the replacement set is given by the following. Recall that by definition 4.1.3, the replacement set is the set for which the equation is defined. In this case, we choose the set of complex numbers minus the set containing 0 and negative 4 because when x equals 0, 1 over 0 is undefined, and when x equals negative 4 plus 4 equals 0, giving us another undefined fraction. Next, we will find the least common denominator. If you are asking what is the LCD, it is the least common multiple of the denominators. You may want to check the video lecture number 2 for more discussions on the LCM. Looking at the denominators, we can conclude that the LCD is x times the quantity x plus 4. Next step will be to multiply the LCD to both sides of the given equations. Now, x times the quantity x plus 4 when multiplied to 1 over x gives x plus 4, while x times the quantity x plus 4 when multiplied to 6 over x plus 4 yields 6x. In the right-hand side, the LCD times 1 is x times the quantity x plus 4. The resulting equation can be simplified into x squared minus 3x minus 4 equals 0. Factoring the left-hand side yields the quantity x minus 4 times the quantity x plus 1 equals 0. By the zero-factor theorem, we can equate both factors to 0, giving us x equals 4 and x equals negative 1. Before concluding, we have to check if the obtained values are in the replacement set. Notice that these values are not in the restriction, which implies that they are in the replacement set. Therefore, we obtain the solution set, which is the set containing 4 and negative 1. Now, consider 3 over x plus 2 plus x plus 2 over x minus 2 equals negative 12 over x squared minus 4. Note that in the right-hand side, x squared minus 4 is equal to the quantity x minus 2 times the quantity x plus 2. This is by difference of 2 squares. From here, we define our replacement set to be the set of complex numbers minus the set containing negative 2 and positive 2. This is because negative 2 and 2 are the values which will make the denominators 0. For the next step, it is easy to see that the LCD is the quantity x minus 2 times the quantity x plus 2, which is simply x squared minus 4. Now, we will multiply the given by the LCD. This gives us the following equation. This is obtained by using DPMA and FOIL method. Combining like terms, we get x squared plus 7x plus 10 equals 0. By factoring, we can write the quantity x plus 5 times the quantity x plus 2 equals 0, and by using the zero-factor theorem, we have x plus 5 equals 0 and x plus 2 equals 0. Solving for x gives us x equals negative 5 and x equals negative 2. Notice that the second value of x is in the restriction. This means that we have to reject x equals negative 2 because it will make the given equation undefined. Therefore, the solution set is the set containing negative 5. For our last example, let's take a look at 2 over 2x plus 5 minus 2x plus 3 over x plus 1 equals negative 3 all over 2x plus 5 times the quantity x plus 1. Our replacement set is the set of complex numbers minus the set containing negative 1 and negative 5 halves. On the other hand, our LCD is the product of 2x plus 5 and x plus 1. Multiplying the given by the LCD gives us 2 times the quantity x plus 1 minus the quantity 2x plus 3 times the quantity 2x plus 5 equals negative 3. Note that this product is equal to 4x squared plus 16x plus 15. Thus, we have 2x plus 2 minus 4x squared minus 16x minus 15 plus 3 equals 0. Combining like terms gives us negative 4x squared minus 14x minus 10 equals 0. As you can see, the numerical coefficients of the terms in the left-hand side are divisible by negative 2. Thus, by dividing both sides of this equation by negative 2, we get 2x squared plus 7x plus 5 equals 0, which is just the quantity 2x plus 5 times the quantity x plus 1 equals 0. Using the zero-factor theorem, we may equate both factors to 0. This gives us x equals negative 5 halves and x equals negative 1. Observe that negative 5 halves is in the restriction. This means that we have to reject this value of x. Similarly, since negative 1 is also in the restriction,
we have to reject. Therefore, because there are no other values of x, the solution set is empty. This marks the end of our discussion. Thank you very much for listening, and I hope you have learned more about equations in one variable. Good luck and see you in MSU.